introduction. And first of all, I thank all the organizers for giving me a chance to speak this nice conference. And okay, today I will talk about some blow-up criterion for the simplified Ericksen-Leslie model and the related equations. And this is a very simplified model proposed by Chun Liu and Pang Ha-rin. And
업다운을 하셔야 돼요.
아, 예. 자, 고맙습니다. And first, I would like to speak about some simplified Ericksen-Leslie models, and I would like to introduce some blow-up criterion in 2 dimensions and 3 dimensions. And I would like to introduce some chemotaxis fluid model, and I will introduce that kind of models, and also I would like to present some blow-up criterions. In some sense, they have some similar structures, but there is no physical similarity. And first, the Ericksen-Leslie model, and this workshop's theme is liquid crystals, and the Ericksen-Leslie models was introduced many times in this conference, and the hydrodynamic theory of liquid crystals, and using velocity vector and direction vector of the fluid, and the Ericksen, and actually initiated by Ericksen and completed by Leslie. They describe the dynamics of the nematic liquid crystals, and this is the following model is just the mathematical models. In some sense, it's just preserving the nonlinear structures, some nonlinear structures, but ignoring some rotation effect and the other stretching effect of the direction field. And so this is the first is the Navier-Stokes equations, and also this is the equations, the Ginsburg-Landau flow, and this is the approximating models. And if we consider the limit problems, and then we have this kind of harmonic map heat flow coupled with the Navier-Stokes equations, and this one is some inner product of this one, and this is the ij component of this matrix, then this is di d, and inner product with dj d, and this is the harmonic map heat flow. So mathematically, these two very important equations are coupled, and then the existence of the weak solution is one of the open problems, and it was resolved by Min-Chun-Hong here, Professor Min-Chun-Hong here, for the whole domain, and Pang Ha-rin and Jin and Lin and Sungkyungwan and proved the global in time existence of weak solutions in the bounded domain in R2, and Min-Chun-Hong proved the existence of the weak solutions, global time in existence of the weak solutions for the whole domain R2, and with a different method. And also tomorrow, the Min-Chun-Hong will talk about some global existence of weak solution for the system of Osin-Frank models, and I will use this kind of function space introduced by Professor Hong, if there is some constant vector and d minus a is in HM, R2 and R3, and the length of d is just 1. And I will introduce the previous kind of some blow-up criterions and regularity criterions. And Hong himself, in the same paper, he introduced some kind of regularity criterions. If there is some kind of small r sub naught is small, and if for any r which is less than r sub 0, and if this quantity is less than some small constant epsilon sub 0, then the solution and ud and in R2 the solution is regular up to capital time T. So if there is no concentrations, then we can have the regular solutions. And also there is another blow-up criterions like that. This is the direction field, and the gradient d, the L4 in space and L4 in time, this norm is bounded, then the solution is regular up to time t. This is done by Lin Wang in 2010. And also there are many other regularity criterion results, blow-up criterion results. And one is that is done by Huang and Wang. And if the omega is the curl of u, this is the vorticity, and so in 3 dimensions, this is kind of Villers-Cottom-Ida type criterions, the N-infinity norm of the omega and gradient d, the N-infinity norm of gradient d and scale. This is, if this is finite, then the solution is regular up to t, and this is in 3 dimensions. And actually, the gradient d, if we consider the scaling, then gradient d has the same scaling with the fluid velocity u. And also in 2D, in 2 dimensions, the Navier-Stokes is regular. And also if we control these terms, so gradient d, the N-infinity norm of the N-infinity in space and L2 in time, this quantity is finite, then the solution is regular up to time t, capital T. And also I would like to introduce some other results. Then Liu and Zhao in 2012, and they obtained they can replace the previous result by they replace the N-infinity norm by some kind of Bezoff space, and also they have some denominator, some kind of log factors. And also setting type regularity criterion in 3D was obtained by Chen and Tan, and LQ in space and LP in space and LQ in time, and also gradient D is in the same space, LP in space and LQ in time. This quantity is finite, and 3 over P plus 2 over Q is less than or equal to 1, and P is greater than 3. Then the solution is regular up to time t. And I would like to mention that this is the scaling invariant class, 3 over P plus 2 over Q equals 1. And let me consider some kind of this one, and this is the kind of some blow-up criterions. And for dimension 2, we can replace N-infinity norm is bound by BMO, bounded mean oscillation norms. This is a kind of logarithmic improvement of the previous, and actually this was already done by Liu and Zhao, and this is some kind of the Bezoff space, and actually so for 2 dimensions, if we control this term, then we have, if this quantity BMO in space and L2 in time, if this quantity is finite, then the solution is regular. And also, if the T star is the post blow up time, then this quantity should be equal to infinity. And also in 3 dimensions, if T star is maximal existence time, if T star is finite, then this quantity should be equal to infinity. Actually, the proof is very simple, and if we have this kind of just using the integration by parts, then we have this kind of estimates. We have HS, S is greater than n over 2, n is the dimensions, and so we have this kind of estimates. And then if we use this kind of logarithmic inequality, and this was done by many mathematicians, for example Ogawa or other peoples, there is some half pattern. So L-infinite norm can be controlled by BMO norm and the log and half. And then if we replace all L-infinite norms by this kind of BMO norms, then we have, then by using the Gruner's lemma, and in 3 dimensions we have this one, and for 2 dimensions we have this kind of double exponential growth for the. So if this term is controlled, or this term is controlled, then we can control these terms, all these terms. Then we have some regular solutions. And let me see. So one factor is that if we, and this is another scaling invariant class. So if we control the omega, so this is the vorticity and the curl of U, and in 3 dimensions, if the T star is maximal existence time, if this is finite, then we have, if we control these 2 quantities, or if T star is the first blow up time, then this quantity should be equal to infinity. And so and P and Q should satisfy this one, and 3 over P plus 2 over Q is less than or equal to 2, and P should be greater than 3 over 2. And this is and so this quantity 2P and 2Q satisfies 3 over 2P and 2 over 2Q is less than or equal to 1, and 2P is greater than 3. The same in the and so this is the, I would like to mention that this is the scaling invariant class. And actually the proof is the very standard. It's just using the estimates. Actually, frankly speaking, we should estimate the higher norms, but I would like to just mention that this first one and actually the other terms and the other equations can be estimated. Other inequality can be derived with similar estimates. And if we control these 2, and then we have, and I would like to show the estimate of this term, and we can just using the Helder inequality and the Young's inequality, then we can have this 1 over A factor, and this one can be observed to the left hand side, and we have this one, and then using the interpolations, then we can we have this one, and using the Young's inequality again, then we can observe this term. We can observe this term to the other inequalities, and also we have this factor, and then this one satisfies the previous inequalities, and Q is just the number 3 over P plus 2 over Q is equal to 2. Okay, and I would like to skip other estimates, and also I would like to introduce some probe criterion in 2D. And if 2D and initial data is in this good space, and M should be greater than 1, and then if T star is the maximal existence time of the local existence of classical solution, if T star is finite, then, and this is the first probe time, then we have this quantity should be infinity. And so this one say the LP in space and LQ in time, this is infinity. And so this is 2 dimensions. We have 2 over P plus 2 over Q is less than or equal to 1, and P is greater than 2. So actually if P is 2, then we have Q is infinity and L2 in space and L infinity time, and we have a priori this L2 in space and L infinity in time, no quantity is bounded, but already this kind of equation has to blow up in finite time, and so if P is 2, so P is 2 cannot be included in this case, and but if P is slightly greater than 2, and also Q is some number satisfying this one, then if this quantity is finite, then the solution is the regular. So actually for the proof, this is again standard, using the standard a priori estimates, and so L4 in space can be controlled by if P is between 2 and 4 and 4 and half, 4 and infinity, then if we divide these two cases, and then if we control this, if we use this kind of interpolations, and then we can control this convection term, this convection term can be controlled by this one. And so this one can be estimated by using the L2 estimates of the heat equations. Then we have this kind of inequalities, and then using the interpolations, and we will observe this one to the left hand side, and also again we will use this kind of inequalities, and we have these terms, but this term is already finite, because in the a priori estimates U is in the L infinity in time and L2 in space, and also gradient of U is in L2 in space and L2 in time. So from the a priori estimates, we already know this quantity is finite, and we have some uniform bound of this one, and then so we can conclude this term is finite. Then it implies if D is in some gradient D is in H1, and then gradient D is in BMO. So this term is this quantity is also finite. And then if we use the previous propositions, then we have the probe criterions. And so in some sense, in 2 dimensions, only the nonlinearity is from the harmonic map heat flow, because the Navier-Stokes equations is regular in 2 dimensions. And so let me see in 3 dimensions. In 3 dimensions, let's consider some kind of the Stokes systems, and we replace the Navier-Stokes equation by Stokes equations, and then in this case, we can have this kind of blob criterions. So if we only control the direction field, the harmonic map heat flow, the D and gradient D is in BMO, bounded mean oscillation space, and the L2 in time, and if this quantity is finite, then the solution is regular up to time t star. And actually the proof is not so hard, because if we take in curl, then we have this kind of linear equations, and then taking L2 product, then we have this one, and also, and for this one we use this kind of identity, and also we have another equations like that, and then we can estimate these 3 terms. And if we add these 2 terms, then we have this one, and then we can estimate these 3 terms by using the Young's inequality and the interpolation inequality, and almost the same, and Young's inequality and the interpolation inequality and Holder inequalities. Then, so combining these things, then we have this kind of estimates. So we can have, if we control this, if we control these terms, then we can control all these terms. And for the higher estimates, similarly, we can do the same things using the commutator estimates, and we can control every other terms, and I would like to skip. So collecting all the estimates, then we have this kind of estimates. So if we control this one, if we take integrations in time, and if we control these terms, then we can control all these terms. Then we have the regular solutions. And next, I would like to introduce some kind of chemotaxis fluid models. And this model was introduced by Tubar and Cisneros and Dombrowski and Borgemus and Kessler Goldstein in 2005. And so this model is the modeling of the swimming bacteria, and the bacteria is swimming some kind of fluid, and the fluid motion is described by the Navier-Stokes equations, and we will consider some kind of heavy bacteria. Then the motion of heavy bacteria is affected the motion of fluid by the Bushinescu approximations, and also N denotes the cell density or bacteria density, and then the motion of the dynamics of the cell density or bacteria density is convected by the fluid velocity. And also we have this is the, this is the chemotactic sensitivity, and C is the oxygen. And comparing with the usual Keller-Ziegler models, this one is the C denotes the oxygen density and the oxygen concentrations, and oxygen is consumed by the bacteria. So So usual Calorie model, the chemical is produced by the bacteria, but this model, the chemical, in this case oxygen, is consumed by the bacteria. And Kc denotes the consumption rate of the oxygens. And so chemical or oxygen is diffused and also convected by the fluid. And so we have the cell density, bacterial density is also diffused, but it is convected by the fluid. So we consider the divalence incompressible fluid, and the problem is that the nonlinearity is not so easy, and so we only have the a priori estimates just from these equations from the maximum principle, and if we multiply C or C to the p minus 1, then we can control any LP norm, LP space time. For example, L infinite space time is finite and controlled by some initial data. And also we have some mass conservations. If we take integrations, then we have the L1 in space and L infinity in time is finite. Okay, so but the problem is that the a priori estimates is not so sufficient to show the existence of the weak solutions. And so to show the existence of the weak solutions, we need some kind of conditions. For example, and Liu and Roth, even if in 2 dimensions, this is a result for the 2 dimensions, and if we consider 2 dimensions, and Liu and Roth saw that in 2011 they showed that the global in time existence of weak solutions if this quantity is non-negative and this quantity and the derivative of these 2 quantities, this is a chemostatic sensitivity and this is the oxygen consumption rate, and this is positive, and also this is the second derivative is negative. And actually Winkler in 2012 and showed that in 2 dimensions and global in time existence of classical solutions, if this quantity is all this quantity is non-negative or positive, and also this second derivative is the negative or equal to 0. And actually their conditions are different, slightly different, but there is no inclusion between these 2. And also if you and this is the global in time existence of weak solutions, and this is the global in time existence of classical solutions. And also Myung-Ju Chae here and Sungkyungwan and here also and myself show that the global in time existence of classical solutions, if there exists some constant mu such that the chemostatic sensitivity and some oxygen consumption rate, and this supremum can be, if this is small, then we can show the global in time existence of the classical solutions. But every these three need some conditions on the chemostatic sensitivity and the oxygen consumption rate, and actually all these 3 conditions are necessary for the good a priori estimates, for obtaining some good a priori estimates. We need these kind of estimates. And also I would like to introduce some flow if L infinite in space and L2 in time, if this quantity is infinity, if T star is finite maximal time, and then if this quantity is infinity, then we have this quantity should be infinity. And also if T star is the first maximal, the first blow of time, then in 3D, this quantity, this can be replaced by some kind of Villers-Cottomade type criterions, omega, and also this one is L infinity, and L infinity in space and L2 in time is infinity. Then we can, if T star is the first maximal time, then this quantity should be infinity. And I would like to introduce some kind of proof. This proof in the if we consider some a priori estimate, and for this kind of a priori estimates, and if we have if we have this kind of a priori estimate, just this is integrations, and using the integration by parts and the Hölder inequality, and this term can be controlled because C is a priori we have the boundedness of C, and the chi C is also bounded, and so this is some kind of bounded number. And then we have using Young's inequality and Hölder inequality, then we have this one. And so for the estimates of C, then we have the L infinity norm of gradient U and the L2 norm of gradient C and scale, and then using the Young's inequality, and also again C is bounded and Kc is also bounded, so this is just the L2 norm of the N and the equivalent to the L2 norm of N. And then again for the fluid, if we take these kind of things, then we have, collecting all the estimates, we have this kind of estimates. So if we control these two terms, and if we control the time integral of these two terms, then from Grunner's inequalities, we can control these terms. And in 2D, and we can actually in 2 dimensions, we can control this one, the time integration of this one, because if we consider these estimates, and so this term can be observed to the left hand side, the previous inequalities, and also using Hölder's inequalities, and then we have this one, and then we can observe these terms to the left hand side, and then if we control the time integral of these terms, then we can control the time integral of this one. So in 2 dimensions, if we control only this term, the time integral of this term, then we have the regular solution up to that time. And also we can improve this kind of the previous blob criterion by these ones. If T star is the finite maximal time, then this should be infinity. And the 1 over P plus 1 over Q is equal to 1, and P should be greater than 1. And this is for 2 dimensions, and this is only for 2 dimensions. And also, if T star is maximal time, then this one should be equal to infinity. So I already mentioned that so P over Q, in this case, P over Q satisfies this number, 2 over P plus 2 over Q is equal to 1, and P should be greater than 2. So this is, in some sense, this is very critical, and I already mentioned that we have a priori, we have the L infinity in space and L1 in space and L infinity time norm is finite. We have a priori estimates, but the one space, if P is 1, then Q is infinity, but this case cannot be included this kind of blow criterions. But there is some special case. For example, if we consider L2 in space and L2 in time, if this is a finite, and this is some kind of, if we control this one, and this is L2 in space and L2 in time, if we consider this quantity, and then we can interpolate these two, and this one we already have the finite, and this term is finite for the weak solutions. So from our blow-up criterions, we can find that the Zhang Guoryu and Alexander Roach saw that the global in time existence of weak solutions, and their weak solutions has the regularity gradient of square root of n is L2 in space and L2 in time, and from that kind of weak solutions, and actually their weak solutions, if the initial data is in good space, good function space, then their weak solutions is already classical solutions. So in some sense, their weak solution is just classical. But and let me see some proof, and just the L2 in space and time, then just the L2 estimates of the heat equations. We have the initial data, and also we have these estimates. If we consider this heat equation, if we use the heat equation estimates, because C is bounded and Kc is bounded, so this is just n, and we have this convection term, and so if we control these two convection term, L2 in space and L2 in time, then we can control the L2 in space and L2 in time of the Laplacian C. And then if we control this one, this is almost same as the L infinity norm of gradient C, L infinity in space and L2 in time norms. If we control this one, then we can have the global regularities. And if we control this one, then let me consider this one, and then just this is L2 in space, and also we can just interpolation inequalities, and also if we interpolate these two, and at first we should have the Helder inequality, alpha in space and alpha space, and then we use the interpolation inequalities, and then Young's inequalities, then we have this one. And so we should control these L infinite, L2 in space and L infinite time norm of U, and this one is already finite, and also we should control this one. And then, but if we see NPT norm, L2 in space and NPT time norm, it can be controlled from the energy estimate. This one can be controlled by the L2 space and time norm of the N. And then, so we can control this one. And then we have, and also if we control these two, then we have, and then let me consider these equations. And then if we control the gradient n, L2 norm, just using the Young's inequality, we have these two. And then if we use the interpolation inequality, we have this one. And then also just using the Young's inequality again, then we have this one. And this one is again controlled. And if we control these terms, then we have, so okay, so this quantity can be controlled by this one. This one can be observed to the left hand side, and also this one can be replaced by the L2 norm of the n, and also this is already finite, and also this can be replaced by the L2 norm of the n. And then, so if the L2 norm of n is finite, then we can control this one. And then also if we control this one, so this is already finite, and using the Groner's inequality, then we can control these things if this is finite. So this is the end of talk. Thank you for your attention.